This is the OJAP Talks by the IEEE Open Journal of Antennas and Propagation.
Welcome to the podcast series by IEEE Open Journal of Antenna and Propagation. I'm Qammer Abbasi, serving as a reader in the James Watt School of Engineering at University of Glasgow. I'm also serving as the founding associate editor and also the track editor for IEEE Open Journal of Antenna and Propagation. In this podcast today, I'm excited to host Professor Kwai-Man Luk, who is serving as a professor in the City University of Hong Kong and is fellow of IEEE Electromagnetics Academy. His interests include design of patch, planar, and dielectric resonator antennas, microwave and antenna measurements, and computational electromagnetics. He has published hundreds of top-notch conference and journal papers on antenna design and have also got 12 patents on the design of a wideband patch antenna with an L-shaped probe. Today, we will focus on some of the prominent issues faced by antenna and propagation community to facilitate them in their ongoing and upcoming research. Professor Luk will share his expert opinion, views, and tips for the career path of researchers, authors, and students who are working or willing to work in the field of electromagnetics, specifically in the design and development of millimeter wave-based antennas. Welcome, Professor Luk.
Thank you, Professor Abbasi, for the kind introduction. It's my pleasure to join this conversation.
So, Professor Luk, I will be asking you some of the questions today, and we want your expert opinion around those hot topics and questions. So my first question is, what are the benefits of millimeter wave antennas, and why is it important for future communication technologies like 6G?
Well, wave antennas are much smaller in size compared to microwave antennas, operating at around a few gigahertz. They can provide much wider absolute bandwidth, even with a few percent of impedance bandwidth. To solve the problem of high atmospheric losses in microwave frequencies and millimeter wave frequencies, high-gain antennas should be used. In fact, compact wave antenna arrays with high-gain and beam-steerable capability are in high demand for future mobile communication systems, including the 6G, of course, operating at wave and terahertz frequencies.
Thank you. For the OJAP research community, what are the current trends in millimeter wave antenna design, in your opinion?
Well, I think high-gain beam-steerable or reconfigurable wave antennas are of current research interest. Various approaches are being adopted. Classical techniques including phase array techniques, Rodman lens, Lumber lens, reflect array, transmit array, Fresnel plate, and Fabry-Perot cavity antennas. Modern techniques include metamaterial and metasurface antennas. Challenging issues that needed to be solved, including wide scan angles, high efficiency, and low fabrication and material costs. In parallel, integration of high-gain transmitting and receiving antenna arrays for achieving compact size is also challenging. It is attractive for millimeter wave satellite internet applications at the moment.
So let us talk about your two recently published excellent papers on liquid patch antennas and vertically polarized end-fire magneto-electric dipole antennas. Can you please tell us what is the difference between both antennas and what are their use cases?
Yeah, actually, these are two different research areas, but represent my current research interests. The water patch antenna is operated as a microwave patch antenna with the metallic patch and the ground plane replaced by two water layers. I would say two thin water layers. Due to the high dielectric constant of water, waves can be trapped in the region between the two water layers. So conventional microstrip antenna operating principle can be realized. A transparent antenna can be realized, of course, now with water. Water is transparent, you know. If the container of the water is made of plastic material, a flexible antenna can also be developed. Currently, the water layers cannot be too thin, and we are now actually searching for other liquids that have higher permittivity and or permeability. If successful, we can develop a very thin liquid antenna. And then about the second one, about the vertical polarized wave N5 ME dipoles. They are suitable for mobile devices as they can be mounted at the edges of a mobile device, such as a mobile phone, for high data rate short distance communications. In fact, we have also modified the design with dual polarizations, so the latency of data communications can be reduced with the use of polarization diversity techniques. So I think I hope I have answered this question well.
Yeah, thank you, very well, very well. So my next question is for the new researchers actually. So what is the ongoing research work you and your team is doing, and can you please share some of the exciting hot research areas for the PhD students and researchers to work on?
I have been so fortunate to recruit about 8 outstanding PhD students joining my team. So they are working in several areas. And most of them are working on antenna designs based on the ME dipole or magneto-electric dipoles currently. Although this technique has been investigated by my group and many other scholars over the years, there are still many interesting things I think that can be done. I consider the current version, so the substrate integrated ME dipole, as a kind of new microstrip antenna with improved performance. So anywhere you think microstrip antenna are suitable, you will find ME dipole can do a better job. My students are working on reconfigurable antenna arrays, so-called the spherical fabric resonator antennas or open resonator antennas, and also working on metasurface with arrays for achieving high gain and wide bandwidth. Other students are working on the antenna arrays for medical imaging and energy harvesting. Frequency range of these ME dipoles cover from microwave, millimeter wave, and terahertz frequencies. Because I have a colleague who is an expert in nanotechnology and microfabrication, so we can see, or I should say Professor Pan, my colleague, she can help us to build very tiny antenna operating at very high frequencies. And this summarizes the current research topic of my team.
Thank you. Thank you. So you talked about metasurfaces and arrays. So a topic which is getting so much attraction these days is reconfigurable intelligent surfaces. So do you think that these reconfigurable intelligent surfaces will be a game changer technology for future communication?
This is an exciting new topic that I think will find a lot of applications in the future, including mobile communications, sensing, energy harvesting, and wireless power transfer. I believe we antenna engineers can make important contributions in this area, although it is a multidisciplinary area requiring experts in communications, digital control, IC design, sensing, to name a few. For us, we can contribute wideband and multi-band antenna elements with a wide range of phase and magnitude control. One of my students is investigating the use of the ME dipole in this area. I know other colleagues or other scholars, they mainly employ the microstrip antenna, but I believe ME dipole may be able to do a better job. Yeah, we're just trying. Yeah. But this is an exciting area, I would say. Yeah.
Yeah. So one last question is, what do you think, which challenges should a researcher consider towards designing the future generation millimeter wave based antenna? So you have a wide experience in these areas from more than 30 years. So what are the recommendations you give to researchers to consider while designing these millimeter wave antennas?
Well, this is actually a difficult question, challenging question. And my experience that my prediction usually is not very accurate. But anyway, I would like to share my view here. In addition to achieving wide bandwidth, several other issues are needed to be reminded. For high performance wave antenna designs, the antenna should not be designed separately. I would say they cannot be designed separately. They should be co-designed with integrated circuits, such as the antenna in package or antenna on chips techniques. Yeah. The total thickness of the antenna structure should also be as small as possible. Otherwise, the antenna will be limited in application. So the size, the thickness should be considered in particular, even at very high frequency, right? And in the design of beam steerable and reconfigurable arrays, which is a very hot topic, I think we should be reminded that the component and material losses should also be of major concern. Otherwise, the arrays will be very low in radiation efficiency, even they can be scanned over a wide range of angles. So I think as an engineers, we need to consider not only the design performance, we should also consider the causes and other issues in real application. And this is my observation. Yeah. I hope this can answer the question well.
Yeah, no, indeed, that was very thought provoking, and I would like to really thank you on behalf of Team OJAP for your time and giving us such a brilliant tips based on your vast experience in this area. And I'm amazed to listen to what you mentioned, what your team is working on, a very diverse range of applications for millimeter wave antennas and race. So with this, I would like to conclude this podcast and would like to thank you again for your time and brilliant answers. So thank you so much.
Many thanks, Professor Abbasi, for your valuable time. Yeah. Thank you very much. Yeah.